as well. So, أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. So, Ruki and O'Reilly's model. Well, we'll do a quick recap here. What we looked at was the first of all, one of the architectures put forth by Dihane and Shingus. The idea is that within this within their model, they were looking at new ways of choosing a rule. So either you abandon a rule that does not work, you change a rule when there's a negative feedback in response, okay? And apart from that, you then understand the probability of the positive reward, if I've got that correct. Rapid rule change after negative reward, ability to memorize previous tested rules. Sorry, ability to memorize previously tested rules, and ability to reason and reject some rules a priori. Competition within each input cluster, competition between intention units, output is gated by a go unit, rule coding units gate memory to intention links, error inhibits the current value generator of diversity proposes alternative rules. What we're interested in looking at is how this applies to the Wisconsin in of itself. So the functional analysis of the task is an important contribution of the work. While the model appears ad hoc as necessary or overly task specific, DNC, the authors, provide neural support for each component of their model. Inhibition and competition result in the auto-evaluation network acting as a generator of diversity. Let's just change something. Transmission, transmission. Okay, yeah, up and running. So, inhibition and competition result in the auto-evaluation of network acting as a generator of diversity. Okay, principles such as competition within subsets of units are shared. Principles such as competition within subsets of units are shared with Cohen Stroop model and are now standard in interactive activation competition networks. The model is not applied to any quantitative data, but lesioning the model supports the view that frontal behavior results from impairment in the network in the reward network, now associated with basal ganglia dysfunction. So, what we're gonna do tonight is simply look at the paper that I was wrestling with the most, right? Which is this one. So, Rugia and O'Neill. Okay, what I'm gonna do is have the slides side by side with the search paper. Such, and the search paper is here. That's the one we have. Right. Okay. So, Bismillah. Learning representations in a gated prefrontal cortex model of dynamic task switching. So, learning representations, what does that mean? So, understanding how stimulus is picked up by the system and how one learns rules and can function with respect to the prefrontal cortex in a gated prefrontal cortex, because we know that the PFC is extremely important when it comes to looking at the Wisconsin card sorting test, because the prefrontal cortex is responsible for task switching, decision making, so on and so forth. Right. Of dynamic task switching. Right. So abstract. We'll read the abstract, then we'll go through this step by step, inshallah. So let me actually try and switch this in a different view. This might work. Let's see. Because slides are no. Let's go back to where we were. So the prefrontal cortex is widely believed to play an important role in facilitating people's ability to switch performance between different tasks. That's what we mentioned. So PFC is widely accepted as the main driver of people's ability to switch tasks. People's ability to switch performance between tasks. To switch performance. Right, let's get that right. Switch performance between tasks. Okay, so with that in mind, we present a biologically based computational model of PFC that explains its role in task switching in terms of the greater flexibility confirmed by activation based working memory representations in the PFC, as compared with more slowly adapting weight based mechanisms. So, what's going on here? So, what they're looking at and what they are presenting is a biologically based computational model of the PFC that explains its role in task switching in terms of the greater flexibility conferred by activation based working memory representations in the PFC. Activation based working memory representations in the PFC as compared as compared with more slowly adapting weight-based memory mechanisms. So am I right in assuming that they're looking at activation of representation as compared to weight that is put on the memory system? That's what I think that's happening here. We'll double check that. Specifically, we show that the PFC representations can be rapidly updated when a task switches via a dynamic gating mechanism based on temporal differences. Okay, so specifically, we show that the prefrontal cortex representations can be rapidly updated when a task switches via dynamic learning mechanisms. Showing that PFC representations can be rapidly updated when a task switches via a dynamic gating mechanism. And a task switches via a dynamic gating mechanism. I'm not sure what that exactly means. Gating mechanism. Based on temporal differences, reward prediction learning mechanism. Based upon, so the element of time difference and reward prediction. Temporal differences, reward prediction. Okay, reward prediction, reward prediction learning mechanism. Learning mechanisms. Unlike prior models of this type, the present model develops all of its internal representations via a learning mechanism as shaped by the demands of the continuous periodic task switching. Unlike prior models of this type, the present model develops all of its internal representations. Present model develops all of its internal representations representations via learning mechan- mechanisms as shaped by the demands, okay, of of continuous periodic task switching. This advance opens up a new domain of research into the interactions between working memory, task demands, and the representations that develop to meet them. Right. Results on a version of the Wisconsin card sorting task are presented for the full model and a number of comparison networks that test the importance of various model features. This advance opens up a new domain of research into the interactions between working memory task demands and the representations that develop to meet them. Results on a version of the Wisconsin card sorting task are presented for the full model and a number of comparison networks that test the importance of various model features. So this advance opens up a new domain of research into the interactions between working memory task demands and the representations that develop to meet them. Okay, so new domain of research into the interactions between working memory task demands and the representations that develop to meet them. Okay, so results on a version of the Wisconsin or WCT are presented for the full model and a number of comparison networks that test the importance of various model features. Results on a of version WCST presented for the full model and a number of comparison networks. Okay, and a number and a number of com comparison networks that test the importance of various features. Okay, so model features. So feature is something that allows us to work and understand the model. Okay. Furthermore, we show that a lesioned model produces preservative errors like those seen in frontal patients. Do we remember what preservative means? Repetition of particular response regardless of the absence or cessation of a stimulus. It is usually caused by brain injury or other organic disorders. Okay, so they have a lesion model as well, which is interesting. Don't know why my glasses are a bit blurry. I'll be back in a sec. Bismillah. Okay, so much better. Now, moving forward. Introduction. We've probably all had the experience of trying to open a door that should be pushed or vice versa. When it doesn't work, you have to switch your approach and try the opposite maneuver. Sometimes, however, you might catch yourself failing to switch and retrying the incorrect maneuver again. This kind of preservation behavior is a hallmark of patients with prefrontal cortex damage. Classic task for demonstrating involvement of the PFC in task switching is WCST, though the literature on this remains somewhat controversial. Further evidence of PFC involvement in task switching comes from tasks related to the WCST, including tasks demonstrating task switching impairments in children, presumably due to PFC immaturity, and other kinds of task switching paradigms. Okay, interesting. So now you have children. Despite this evidence for the involvement of the PFC, the precise mechanistic role of the brain area in task switching remains unclear. In this paper, we present a biologically based model performing WCST-like tasks, switching tasks that helps to eliminate the mechanistic role that the PFC plays in switch tasking. Okay. Specifically, our model is founded on the idea that PFC is specialized for activation-based working memory. Right, so what's activation-based working memory? Working memory is what's memory being used, collection of facts in the moment. But what is actual What is actually activation based working memory? Okay, it's these for now. Okay, so the model is essentially based upon the activation based working memory. Model is founded upon the idea that PFC is specialized for activation based working memory. Okay, so let's quickly look at what this is. Activation based memory this is better. Okay, activation based models of working memory posit that working memory is not a separate buffer or store in the memory, rather temporary elevated activation of representations within long-term memory or sensory systems. So we need to write this in red. Activation based working is not a state that working is not a separate buffer or store in the brain. That's all. But rather temporary, rather temporary elevated activation of representations within long-term memory-based systems or sensory systems. Okay, sensory systems. Okay, so this is what we're looking at, is that activation-based memory, working memory, is not a buffer or stored in the brain, but rather it's a temporary elevated activation representation within long-term memory systems or sensory systems. This activation is maintained by attention-based top-down control, often involving the PFC, which allows for the active maintenance of information in the absence of continued sensory input. So what's happening is that this activation is maintained by attention-based top-down control, often involving the PFC, which allows for active maintenance of information in the absence of continued memory sensory input. Okay, that's what's happening here. Quite fascinating. So, activation, okay, maintained by attention based, by firstly attention based. You need to have attention on a stimulus, otherwise, it's not going to happen. Top down. So, what does top down mean? It means that a feature of the system relies on the stimulus that is being presented. Okay, specifically a feature of the stimulus that can represent at least the form or the image itself. So, for instance, top down. In this case, I would say you have a red triangle pointing downwards. That red triangle pointing downwards, top down control in visual neuroscience would typically be okay, you have the three corners occupying a space, the lines join together, or 3 points you can think of, and they join together to make that triangle filled with red. That is top down. So you have the conceptual all the way down to the actual. So I think that's what it's confirming as. Let's actually dive a bit deeper. Okay, interesting. So goal driven, voluntary, and intentional. Mm. Okay, it's just nonsense. Yeah, feature integration theory. Okay, top down. Let's go back to what we were doing. So, goal driven, goal driven, looking for object. Okay, often involving prefrontal cortex, which allows the active maintenance, which allows active maintenance, maintenance of information in the absence of continued sensory input. So, key aspects of activation based working memory, we'll go through this. Temporary activation of long term memory. Long term memory relies on activating items already stored in the long term memory. This perspective, often associated with Cohen's embedded process model, suggests that working part of memory, simply the subset or LTM, currently in a high state of activation. Neural mechanisms. Working memory is maintained through the sustained excitatory activity of networks, specifically between the prefrontal cortex executive and parieto-temporal cortices perceptual sensory. So that's your executive functions right here, of course. And you have your perceptual sensory systems. Temporal language plays a role in this place as well. Use it or lose it dynamic. Because the system requires continuous activation, it is susceptible to rapid decay if attention is shifted away, necessitating constant rehearsal or maintenance. So this is very important. Stimuli has to be shown, and it has to constantly be shown something in order to keep it fresh. The synapses, so these are neurons that connect to make this said network, have to be constantly engaged. And this is why people have attention focus when it comes to using mobile phones and screens. What happens is your brain is constantly activated in one dimension. As we saw here, when it comes to the top down approach, beta waves are very important. So, oscillations, beta waves are very, very important. And paper we have here is this one. I think I'll break it down nicely. Yeah, beta frequency here. So this is extremely important when it comes to the actual Wisconsin card sorting test. You have to constantly be showing stimulus to the participant so they're constantly engaged. Limitation in capacity, I guess this is where preservative errors come into as well. The number of items that can be maintained is limited by the total number of source activation available in the brain. If the activation falls below a certain threshold, errors of omission forgetting occur. Activity silent mechanism. While early models relied solely on persistent spiking activity, modern research suggests a mix of active spiking and activity silent mechanisms, synaptic changes that allow for temporary storage without constant high level firing. Differences from other models. Unlike traditional structural models badly hitch, which often view working memory as distinct, separate, short-term store, the activation-based view treats working memory as a functional state of existing long-term representations. So now there's a bit of a conflict here because we are trying to look at working memory, and activation-based memory is the foundation for this paper. But in any case, it's still relevant as per the system that they're proposing here. Right. That's been noted here. One, two. Right. So, by representing information as maintained activation states, the prefrontal cortex can contribute to task switching okay, by rapidly updating these activation states in response to feedback. So what that means is as you're switching through, as your task switching and updating and your states are being activated, pardon me, your activation states are constantly being updated as the feedback is coming through, right? This is what the prefrontal cortex contributes towards. The PFC can contribute to task switching okay by rapid updates of the activation states in response to feedbacks in response to feedback. This activation switching can be much faster, okay, than the structural changes that underlie adaptation of connection strengths between neurons as captured in standard neural network learning mechanisms. This activation switching can be much more faster than the structural changes that underlie adaptation of connection strength between neurons. This activation switching can be much faster than structural changes. This activation switching can be much faster than structural changes that adaptation connection strengths between the neurons, as captured in standard neural network learning mechanisms. This activation switching much faster. Adaptation of connection strength. This activation switching. It says can be. I would say is seemingly faster than the structural changes. Structural changes that adaptation of connection strengths between strengths between. So the underlying structure of connection strength between neurons. So you have a neuron N, and then you have it connecting with another neuron N2. So the strength, which is, let's call it ST, that is weaker. So this structure, for example, is weaker structure, I would say, seemingly weaker than the than the above activation switching. Now, informations PFC can contribute to top switching. So, which is what? Rapid updates of activation states as feedback is responsive, sorry, as responding to feedback. So feedback is, for example, rule. This rule does not work. I need to change. It works, it works, it works. Okay, now I need to change. It works, it works, it works. It doesn't change. I need to change. It works, it works, it works. Don't need to change. Also, I need to change it again. The rule works, but I chose the wrong option. I chose the wrong option. So all of this is happening. Feedback, feedback, feedback. Activation states changing. Okay, activation states are changing by virtue of the activation switching. Okay, and this paradigm is seemingly more potent and faster, because it's faster than when one neuron connects with another neuron. The strength between them and the overall structure that exists is seemingly weaker. So this is a standard neural network learning mechanism. So let's quickly check out what this is. Standard neural network training models involves training models to minimize error between predicted and actual inputs, primarily using backpropagation to adjust networking weights and biases. Key mechanisms include forward propagation to generate outputs, loss function to measure inaccuracy, gradient-based optimization algorithms (SGD), and ADAM to iterate, reduce errors. Okay, I think this is essentially connectionism you're looking at. Yeah, hidden layers, input, blah blah blah. Yeah, that's the stuff we were looking at in Koslin's book, right? So yeah, it's nothing groundbreaking or different, really. Something that we are familiar with, right? Okay, so let me just do this for a second. These components heavy in learning, yeah, where connections strengthen based on activity. So standard network mechanisms. So what are these neural network mechanisms? Optimize artificial weight-based architectures via gradient descent and backpropagation to minimize error. Gradient descent. Gradient descent is an iterative. Iterative? Did I say that? Iteration.
Iterative. Iterative.
Iterative, relating or involving iteration, especially mathematical computational process. Another term for frequentive. Denoting grammatical rule that can be applied repeatedly. Okay, iteration. The repetition of a process or utterance.
Iteration.
Repetition of a process or utterance. Okay, a new version. Repetition of mathematical. Okay, so gradient descent is a repetitive optimization algorithm used in machine learning to minimize the cost function by updating model parameters, weights, and biases in the direction of the steepest descent, defined as negative gradient. It works by starting with random parameter values and taking small, repeated steps downhill, with the step size determined by the learning rate. Core concept formula. The algorithm aims to find the minimum of a function, such as cost j, in linear regression neural networks. The updated rule for a parameter is theta, where alpha is the learning rate and delta j theta, so change in the cost theta, is a gradient of the cost function with respect to theta. So theta minus learning rate times changes in the cost theta. So that's a parameter we're looking at. Use the entire dataset to compute gradient for each step, which is across. Stochastic gradient descent. Okay, these codes. Okay, so involving artificial weight-based architectures, architectures via gradient descent. So that's basically negative gradient. So that's theta equals to what was it? Theta minus alpha multiplied by change in j theta. Okay, and duh, 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 descent and back propagation propagation to error. These computation systems biologically inspired, okay, by Hebbian learning, right? So that's synaptic plasticity, synaptic plasticity, plasticity, synaptic plasticity. Connections get stronger based on activity. Biological global error sequence. So these signals often to delta theta oscillation critical for adapting to changing to changing conditions and associated with neurotransmitter systems like dopamine. That's what Aaron David Reddish speaks about as well, is adapting to neural the dopamine, the cholinergic discharge, ACTH, acetylcholine, is very important when it comes to decision making. Okay, uh, the see different system acts as a global model during prediction across severely widely. The system acts as a broadcast signal for learning and adapting to changes. Application malfunction, error, core feature of psychiatric disorders. Okay, interesting. So there are signals that the mind picks up where there's an error in action or prediction, right? And global signals averages signals aided. Okay, pretty straightforward. So I'm gonna go back to that gradient descent. Okay, so number 5, artificial neural networks depend on global line error signals. Biological ones, however, systems use local associative and unsupervised learning. Okay. This rapid updating in PFC can be specifically triggered by a dynamic gating mechanism that controls the updating of activation-based working memories maintained in the PFC. So the rapid updating in the PFC can be specifically specifically triggered by a dynamic gating mechanism that controls the updating of activation based working maintained in the PFC. Okay, the present model goes beyond earlier models of previous model goes beyond of task searching involving a dynamically gated PFC system. Developing PFC number representation entirely from experience-driven learning mechanisms operating in the context of repeatedly switching set of tasks. Gated PFC. So developing PFC and presentations entirely from experience. Operating in the context. Operating in the context of repeatedly switching great sets of tasks. Okay. Our previous models for PFC function use hand-coded PFC representations, so this represents an important advance that opens up many oh. Nonetheless, we build upon by employing similar nonetheless we build upon with similar dynamic gating mechanism based on the word prediction. Nonetheless, we build upon a similar dynamic gating mechanism. Okay. Unallocated okay. Spaced on prediction mechanism. We begin with a summary of the task, switching task, followed by description. Okay, so task, task, switching task, summary, followed by description. Present results. We present results. Okay, dynamic task we use for is modified version of the widely studied WCST task where inputs are causing features of different stimulus. Okay, stimulus dimensions. Using modified version WCST in, inputs stimulus dimensions. Okay, that would be color shape shape. And the essence of the task is to focus on one of these dimensions for a series of trials and then switch to a different dimension. The essence of the task is to focus on these dimensions, switch to a different dimension, naming task, naming the feature, instead of sorting cards into piles. Thus, we refer to this as the dynamic. Specifically, each stimulus item has 5 dimensions, with 3 possible feature levels each dimension. The goal of the task is to guess an unspoken target dimension. Put the feature value along the dimension for each item. If the model outputs the correct feature value along the target dimension, if the model output the correct feature value along the target dimension for the current stimulus, it is rewarded, otherwise not. The patterns of reward can be used to guide the search for the unspoken dimension. The same target dimension, i.e. the subtask, is used for a period of n trials. Typically n is 50 trials, after which another target dimension is selected, requiring the model to switch to a subtask. The basic strategy to perform this task correctly is a simple win, stay, lose, shift type rule. If a positive feedback is received, continue with current subtask. The same target dimension. Subtask. The basic strategy to perform this task correctly. The basic strategy to perform this task is a simple mistake. Basic strategy. Reshadow the strategy. Okay. So here's what's happening. That's wrong. Small, medium, large. So small, small, the task needs to be featured. Function, features, feature levels. Okay. Figure 2 shows the structure of the model, which has the same basic elements of our previous task switching models and is implemented using the Libra framework for the activation. Field. Sample layer presents the input stimuli using locals. It has to. The essential task that the network must perform is to select one dimension out of 5 impinging on it from input stimulus. The PFC layer facilitates this dimension. This dimensional selection provides top-down support by biasing.
Procession.
Word. PFC facilitates this dimensional selection. PFC layer facilitates by providing a dimension to be selected through, with top-down support or biasing. Okay, given dimension, given facilitates task switching by being able to rapidly update to another dimension. It facilitates task switching update to thereby providing so PFC layer here facilitates dimensional selection. So selection of one of these rows, top-down support. So looking for an object of or biasing for a given dimension facilitates by switching, task switching by being able to rapidly update to another dimension. So it's constantly updating between each other, never providing biases. Thus, as our previous switching models, O'Reilly, Munakata, O'Reilly, the PFC does not contribute directly to the input output mapping task, but rather contributes by providing appropriate task relevant biases. Okay. Interesting. This contrasts with some other task switching models. So Dehaney and Shingus is a completely different model. Now it makes sense. Now it makes sense. Excuse me. PFC layer maintains an activation based working memory. Activation based working memory. Presentation of subtask stimulus dimension relevance. Support this memory to encourage coherent task representation instead of blend of different to enable exploration of explicit instruction task. To enable exploration of explicit instruction. To explore, to enable exploration of explicit instructions, task will also include task input. Task input, PFC updating, and the AC is influenced by the reward-based system. Let me take a note of this. Can I not draw here? Okay, so where's the pen? Base system. So I think it's this one maybe. I think it's here. So gonna write here reward Sometimes support each other as described in the next section. Updating is influenced by the reward-based gating mechanism adaptive critical exciting circles with POC aside from these key spaces. Described in the next section. Updating reward-based dynamic gating mechanism. So what I'm going to do actually is draw an arrow here, so it makes sense about what's being said here. So here, okay, yeah, that should be okay. So this is what we're looking at now. So yeah, okay, during the naming task as described, the task input is uniformly activated so as to not provide any discriminant information about the relevant task. Distinguishing feature characteristics. A function of coefficients of a polynomial equation whose value gets information about the polynomial. Okay, so let me just write this down here. So PFC does not contribute directly to the input output task, or rather contributes, but rather contributes appropriate task relevant appropriate task relevant biases. Okay, contrast with Yang. PFC exercise. The PFC layer maintains an activation-based working representation concept. The PFC layer maintains activation-based. Okay, so let me see. Computation inhibition prior task. This is similar to this actually. What's interesting is I found this earlier today. Churchill's book representing the world. What is find it. I have no idea where it's going. Anyway, so matrices output PFC into PFC. to right. Let's go back to the PowerPoint. After almost 2 hours. Okay. So a model of POC that learns task appropriate context, representation, stimulus, encoding, trigger, activation of output units by hidden units. Hidden units are biased by reciprocal connection with POC. POC modeling by adaptive AC. Task input is held constant, i.e. not used. Developed within Libra. Contrastive heavy learning is employed where learning minimizes the difference between plus minus phases. Pools of units employed K winner takes all dynamics. As we saw, functional motor switches are induced by a dynamic gating mechanism based on the reward on a temporal difference reward prediction learning mechanism. The PFC learns context representation very true. The AC unit learns to expect reward and fires when reward is absent, destabilizing the PFC representations. Function of the mode. So this is following an error. Sequence of context activation within the PFC layer during a task switch. Gray squares represent the inactive units, white squares represent active units, and dark gray squares represents uh, units within a negative bias activity. Specific stimuli 5-dimensional, 3 per the values per dimension. Dimension features, and then you have features levels. Stimuli generated randomly on each trial. Maximum error rate is 250, minimum error rate is 5 per switch. Initially, the model produces epoch number. Okay, so this is what I don't really understand. This particular graph is troublesome for me. Let me quickly ask my GPT agent here. Explain this graph in simplest simplicity. So initially the model produces random preservative errors. Following developmental period produces mainly preservative errors. Once each task has been learned, residual preservative errors occur at each task switch. Random error. Okay, so let's try and understand this in its simplest form. This graph is basically showing starts off making a lot of mistakes, then learns fast. Faster than mistakes almost disappear. What the axis? So x is epoch. How long the model has been training, practicing. More to the right equals more practice. Y is error. How many mistakes it's making higher equals worse. What the three lines means: total error circles, all mistakes are added together. Preservative error squares, the stubborn mistake, the model keeps using the old rule even after the task has changed, like WCST when someone keeps sorting by color even though the rule switched to shape. Random error diamonds, the confused guessing mistake errors that are sticking to the old rule, just inconsistent wrong choices. What happens over training? At the start, left side, all error types are high. The model doesn't know what to do yet, so it makes a lot of mistakes. Early learning phase, roughly up to 20 epochs. Errors drop sharply. This means the model quickly figures out how to handle the task. After that, beyond 20 epochs, the lines sit near zero and stay zero. The lines sit near zero and stay zero. Lines sit near zero and stay zero. That means the model has basically learned how to pick the right response, how to stop clinging to an old rule, how to stop random guessing mistakes. The key message in one line. Training teaches the system what to do and when to switch rules. So total, stubborn, preservative, and random errors all crash down quickly and stay low. Okay, look at the next one here. Oops. The full model, no gate, the full model without the AC unit, no PFC, the full model without the AC or the PFC. SRN, standard simple recurrent network memory. BP, a feed forward network. Let's see what this has to say. Thanks. Attached. The graph is comparing different versions of the model to show which designs learns the task best. What the axes mean. X-axis epoch number, how much training or practice the model has had. Okay, Y is error, how many mistakes made, low is better. Now, what each line represents. Okay, make this bigger for everyone here. Okay. So, go back to, okay. So, PFC, okay. The full model prefrontal cortex, the proper gating maintenance system, the intended design. BP, a basic backdrop style network, good at static mappings, often weak at rule switching and context. Feed forward network, so that's essentially all of that, right? Pushing forward and then pushing further forward. Okay. SRN, a simple recurrent network, has memory, but it's more soft or blurred and can struggle with clean task switching. Okay, so we can see BP is going is the most craziest here. It's weak at switching rules. Second, with the most errors is SRN, SRN blurred struggle with clean task switching. No gate aversion without gating mechanism, so it can't properly decide when to hold versus update context. No NRFC. So no and another damaged version where a key PFC related control ingredient is removed. So context control is weakened. You don't need the exact technical meaning of each ablation to read the point of the figure there. What happens when the control pieces? What the picture is saying. Everyone improves fast at the start. In the first 10 different epochs, all lines drop sharply. Thus, the models went from clueless to getting the basics. Differences show up after the early learning. PFC keeps getting better and stays low. So their model is clearly a successful one. Seemingly so. The PFC line drops to close to zero and stays there, meaning it not only learns but keeps performing reliably. Most other models stuck with a lot of errors. SRN no gate no and RFC flatten out around a higher error level. They improve but not enough. They're still making plenty of mistakes even after lots of training. BP actually gets worse over time. The BP line drops early, okay, and then there's a sharp rise, but climbs back up a layer. This usually means it learns some shortcuts but can't handle dynamic switching, so performance degrades as training continues. Take away one sentence: the full prefrontal cortex plus gating design is the only one that learns the task properly and stays accurate. Task is what? Naming, not just identifying the dimension. When you remove the context control pieces or use simpler networks, errors stay high or get worse. So again, seemingly Ruger and O'Reilly's model is quite a good one. Some yes, almost all errors produced by the station. Okay. Okay, this is quite interesting. So now things are getting in motion. Okay, still nada. Okay, same idea. Epoch error. Lines total error is circles all the mistakes combined. Preservative error, again stubborn mistakes. Random error is again the diamonds, messy guessing mistakes. What happens in the graph? Before the lesions start to epoch about 50, the lesion begins. All errors drop quickly to near zero. So the model learns the task well and performs smoothly. The lesion happens in the middle. Right after that point, the model suddenly starts making a lot more mistakes. After the lesion, preservative errors shoot up and keep spiking the line square. This means that the model becomes bad at switching rules. It gets stuck on the previous rule again and again. Random errors stay low. The diamond line stays near the bottom, so it's not just confused or guessing. It's mainly failing in a specific way. It can't flexibly update its rule context. Total error rises and falls in waves. The circle line. And sometimes partially recovers, then slips up again. Like it can sort of cope, but it keeps falling back into old habits. Simplest takeaway: the model learns fine, but after damage, lesions, it mostly fails by being stubborn, repeating the old rule rather than making random sloppy mistakes. Okay, right, conclusion. Okay, okay. Bisharas. Look at this. This is where we stopped previously, around here. So I'm gonna look in that again and understand this. In fact, I'm going to do this on my own by virtue of now moving forward from here and touching on these two. And okay, right. Well, inshallah, on the next one. لا حول ولا قوة إلا بالله ربنا آتنا في الدنيا حسنة وفي الآخرة حسنة ربي زدني علما ربي زدني علما ربي زدني علما لا إله إلا أنت سبحانك إني كنت من الظالمين